So we're looking at the ambiguous case of sign law today. Okay. A few things start to arise when as I work through this today, you'll see. In any event, sometimes there will be triangles be able to be created, and sometimes there won't be, and sometimes there'll be two triangles that you'll be able to create. Okay, so this will be an interesting lesson today, I think. Okay. So just based on the information that gets provided to you in the question, you're going to try and draw a triangle, right? And those are your three scenarios. No triangle can be drawn, one triangle or two triangles. Okay, so we're just going to suppose that we're given side A and side B and angle A of a triangle ABC. Okay, and we're going to let H equal the height of the triangle. Okay, and then you're just going to remember that H can be found by going like H is equal to B sine A, which is just SOHCAHTOA basically for sine, right? Because it'd be a right angle triangle. So here, let's draw the first one. So we're going to draw a triangle, or somewhat of one. We're going to have angle A down in here. I'm going to draw a side length. Okay. This is going to be H. Everyone agree? That would be the height of the triangle. Everyone agree? Okay. And I'm going to call this side length B. It's going to be call it C. Side length B. All right, let's draw the picture for a sec. Okay. So this is usually always a tough one to teach. Okay. So here's your angle A. Okay. If I actually had a triangle, it would have a side length A opposite of angle A. Everyone agree? The problem here, and what this picture is depicting, is that side length A is not going to be longer than the height of the triangle. And subsequently, you can't create a triangle as a result. Does that make sense? Because that side length A, this one, is never going to touch the bottom. Why is it never going to touch the bottom? Because it's shorter than the height of the triangle. Yes, Sophie.
Should the bottom thing be B, or is it supposed to be 2C?
There's a little bit of, well, there's angle C and then side length C, right?
Which one's which?
Well, the angle is going to be up top, right? And the side length is the side length. Okay. Did you need them for set? Is that just supposed to be in my pile?
No, I'm just wanting one from the pile.
Oh, okay.
Just give me a call.
Okay, does that conceptually make sense so far? So if that little side length A is shorter than the height of the triangle, then that green component is just going to swing around. At no point is it ever going to touch the bottom. Fair enough? Because A is less than H. Right? Everybody see that? That's what that conclusion's drawing there. So side length A is less than the height of the triangle. It never touches the bottom. No triangles can be created in that situation. How could I figure that out? Everything is being found as we work through this lesson today. You're going to figure out what the height of the triangle is. That's going to be your first move. Okay? Once you know the height of the triangle, then you can take a look at the other information that's provided to you in the question and figure out whether or not the other side length is longer or shorter than H and make some conclusions about it. Okay, and what we're going to do on this first page is draw out all the situations that can occur given the height of the triangle and side length A. Okay, so obviously in this situation, no triangle can exist. Okay, maybe I'll highlight this too. H will be the okay, what happens if H is equal to A though? So if I redraw this picture now, I'm gonna have A, C, what happens if this green component, I'm drawing it beside so you can see it. Obviously it would connect. So what happens if the green piece is equal to the yellow piece? No, remember, sorry, the green piece is always going to be that side length A. How many triangles do I get if A is equal to H? You just get one triangle in that situation. Okay? So therefore, one triangle exists. Okay, and again, we're figuring out the height of the triangle using that, right? And that has just been derived from or come from sine of A is equal to opposite over hypotenuse, where the opposite is going to be the height of the triangle over side length B. That's all that's come from, right? Okay. What happens? Oh, we got a third color coming in now. Sorry, I'm going to draw the picture again. What happens if I get a situation like this? This is side length B still. That's angle A. This can be C up top. And we still got our H. And this will be point B. What happens if side length A is longer than, well, we all agree, first of all, we haven't talked about the fact that A is larger than H, but would we all agree that A is larger than H? Okay, so that's a given, right? So a given is, in this situation, that A is larger than H. But that's not what this situation is talking about. This situation is going to talk about A being larger than B. Side length B, right? So you can see, let's try not to mix up the colors. A is going to be larger than side length B. So how many solutions, or like not solutions, how many triangles do I get in this situation? Is there two? Oh, ignoring the height. Just one big triangle. One big triangle, right? The situation of two will come in a minute, and then that'll make sense. You're not really, the height of the triangle isn't really creating another triangle. It's just there as a reference, right? A reference specifically for the first two examples when we're comparing the height, okay? But in this particular instance, when A, the other side length that's given to you, is larger than B, which would also be provided to you in the question, we only get one triangle. Is everyone okay? Typically, I don't think this is necessarily the part. I think everyone conceptually follows along. It's when we start throwing information and you start drawing triangles, and I ask you to conclude how many triangles there are, given the information in the question. That's when things start to go off the rails a little bit. Okay? Is everyone okay? Because this is when things start to get Okay, so H is important here. We're referencing H. A can be larger than H, but smaller than B. Do you know what that produces? That produces two situations. Okay, so side length A. Here, maybe I'll do some highlighting so everything's all clear. Okay, just give me a sec. Sorry, is A supposed to be green? Sorry, I gotta try and keep it consistent. All right, so here's what happens. We're in the situation where like A is larger than H, and so it has to touch the bottom. Is everyone following? So we've established what the height of the triangle is. That's the yellow component, and then we also established that A is less than side length B. And so what that green component has the ability to do now is either be on the right side of that yellow line or on the left side of that yellow line. And subsequently we get two triangles because we don't really know which one it is. Right? That comes into play that the title of the lesson, that ambiguous case of side law.
Would there be like infinite triangles just like that moving A, split in left or right
It has to touch the bottom exactly
at that spot?
at that spot. Yeah. So it can't, that's the problem with this one, right? Like if I go back one, that one can't just all of a sudden, I can't just bring A over here and it's like way out. That's not a triangle anymore. You know what I mean? It has to touch the bottom exactly at its length. You know what I mean? Does that make sense? So I can't take this side length and swing it over here.
No, but for like the second A, can't you move it like slightly right or left?
It will have a specific spot so that its exact length touches the base AB from here to here. Does that make sense? Does that answer your question?
Or couldn't it be anything in between?
It can't be anything in between because it's going to touch at the exact spot where the length comes down. So you're going to have like, what I'm trying to communicate, I suppose, is this, right? So you guys are asking this question, which is fine. That's a totally valid question. But if side length A, let's see if I can do this. I don't think I'm going to be able to do it. Let me see if I can communicate this with the iPad. Everyone in agreement that that's a triangle with like side length A? What I'll do is I'll take side length A now and see if I can swing it. Can you see how like it's only going to touch in one specific spot? When I rotate it, it can't be anywhere. It's just going to touch in one exact spot based on its length. And what I can do is take it and swing it from here to here and I get two spots. But it can't be an infinite number of solutions because, look, it can't be here because it's sticking out over the bottom. So I'd have to swing it just a tiny bit more. And a little bit, ooh, that's getting worse. You see what I mean? It can't be wherever you want it to be. There are two specific spots. That's pretty good, actually. So one of them we call that A prime, that's what I labeled it, and the other one's just going to be A. Everybody see now? And in relation to H, it has to be larger than H, but smaller than B. Sorry, B's not there. That's C. So two triangles get created here. Okay, so all of those have been acute triangles. What are acute triangles? Say it again.
Two angles less than 90 degrees.
Yeah, it's the angles are less than 90 degrees in there, right? And what we're gonna take a look at now, right? Can everybody see that? They're all acute angles. What we're gonna do now is take a look at the obtuse situation, right? So what I'm gonna draw here, so angle A is gonna be obtuse. That doesn't change. I'm still gonna draw angle A down here in the bottom left, except now angle A is gonna be obtuse. And I'm just gonna draw out the situation that they want. So that's still angle C, this is still angle B, and this would be side length B, and subsequently that would be side length A. And this is your obtuse angle. So let's just have a look here. Well, as you're copying that down, I'll do some highlighting and then we can have some conversations here, and I'll just try to keep it straight. Okay, can I ever take this side length A, and make a triangle with it? What's the only instance, which leads us into the next one, but what's the only instance that I can actually create a triangle based on what I've drawn here?
Angle A has to be bigger than angle B,
Not angle,
or sorry, side length.
side length. Side length A has to be larger than side length B. If that's the case, if side length A is larger than, that's probably larger. If that's larger than side length B, right, then I can actually extend it, even though it's not touching at that particular angle, I could swing it down and make it touch somewhere. Would everyone agree that that red line segment is larger than the blue one? Because that's all that's trying to convey there. It doesn't matter where I take this green line segment right now and swing it, it's never going to touch the bottom and create a triangle. Does that make sense? So we're not really referencing the height in the triangle of this question. We're referencing the two side lengths that are provided to me in the question and making a conclusion about that. Okay, so I can't make this swing anywhere to touch the bottom, and so no triangles exist. And obviously the last one is the same picture, but A is going to be larger than B. Everyone agree A is larger than B? So these ones are just comparisons of side lengths, particularly for the obtuse. The rest of them, the acute triangles, you have to make a comparison with the height to decide whether or not there is going to be a triangle created from the information provided to you in the question or not. Okay? Okay, and how do you think we're going to be able to do all this work, these proofs? It's called sine law, so we're going to use sine law probably. But particularly up top of the acute triangles, I'm going to need SOHCAHTOA to determine what the height of the triangle is. Okay, I can hit stop there.